All right, line V1, learn test 9, DC magnetic controls. Once again, don't stress, they're moving some of this stuff around in our modules, but don't stress if it's not line V1 or learning task 9. What it is going to be describe the operation of your DC magnetic controls. So that's what we're going to be looking at, and you should have drawings inside of there that are going to go and look like this. Now, the very first drawing that we are going to go and see is going to be one where we are doing what we refer to as across the line starting. Basically, where we're going to go from line to line, and we see that we have got no paths inside of there that are going to go and limit the acceleration or limit the amount of current that I might have running into this DC motor. Let's identify the type of motor first. The first thing that I see is that I have got a field that is operated in parallel to the armature. Therefore, this thing is going to go and be a shunt type of motor. Second thing that we're going to do is we're going to take a look at a bunch of the components that we have inside of here. Now, these are components that you would have covered in first year and in second year. So if you have questions on more of the operation of them, go back to those modules and take a look. First thing we see over here is we've got the overload itself. This is going to be the overload heater that we are going to go and have. And all that this does is it is going to monitor the amount of current that is going to travel through the circuit. As that current travels through that circuit, it is going to go and create heat. That heat is then going to go and activate a set of contacts over here. And the contacts over here are going to go and be inside of our control circuit that are then going to go and be used to shut off our motor. Does this ever actually open up, this heater? No, this heater itself should always stay closed. We're not trying to interrupt the main current. Think about it. Main current might be, 30 to 40 amps that we are going to go and have inside of here. We don't want to have a contact that's going to be big enough for that. Instead, we can go and just monitor the 30 to 40 amps through heat, and then we can go and use that to switch something that's only rated for maybe 1 or 2 amps, which would be this control circuit here. Second thing that we're going to look at is going to be this. This is going to be a contactor, and then we see that this contactor is going to go and have an associated set of contacts, this over here. We refer to this as 3-wire control, and you covered this inside of your first year where we went through the operation of these. Let's go through right from the very beginning on this one, then we'll go into a bit more complex. First thing we're going to do is we are going to go and close in our switches over here. So I'm going to go and have my main switches. Downstream of those main switches, I see that I have got some fuses which are going to go and protect my motor circuit itself. We're allowed, under section 14, to go and tap off on my main fuses. Even though these ones here are much larger, we're allowed to tap off to smaller ones. We should still have another smaller set of fuses inside of here for my control circuit, but we're allowed to tap off the main. This is now going to go and provide power up to this point. If I were to go and take a look at it, I see that I'm going to go and have opens all over here. So I can see that my positive has been applied all the way up to there because all of those contacts, the start button, the motor contactors are all going to be sitting open at this point. And if I were to go and take a look on the other side as well, I would see that I would have a negative that is being applied all the way through and up to here, but we have no complete path for current flow. So let's go and complete that current flow at this point. When I press my start push button, I'm then going to go and complete my path for current flow that is then going to go and send current through here, through my coil, through that start push button, and back up to here. Well, when it does that, it is going to go and magnetize, energize that coil, which is then going to go and activate every single one of my associated M contacts. Let's start by looking at the ones in the control circuit over here. So we see that that coil is magnetized, which means that it is then going to go and close this one over here. At this point, because it closes, we have a second path through our control circuit that is going to be going through here and through here, which means that if I remove my finger off the start push button and break that one, we have still got this path through here. We refer to this as a seal-in set of contacts over here. Beautiful. So we seal in through there. This is now going to go and give me my start. As soon as I want to stop it, I would just have to press the stop push button, which would break this. As soon as it would break this, it would go and lose magnetism, open this up, and we would be back to where we started. This is going to go and give us what we call low voltage protection, actually. And we're just going to talk about this, actually. There's 2 different types that we have. They're listed inside of your code book as well. We got low voltage protection, and we have got low voltage release. Okay. low voltage protection is going to protect people, is what it is. It's not electrical protection, it's protection of people. And what low voltage protection is that if I lose power to my circuit, it is then going to go and lose magnetic flux, and my contactors are going to go and open once again. Which is going to go and protect anybody. So if there's a power failure, let's say that this shunt motor was running a saw, that saw would go and shut down. When the power comes back on, we're not going to have the saw starting back up immediately. This would be termed as low voltage protection. Low voltage release would be if I've just got 2-wire type of protection, where I'm going to go and have something where it's just a switch. Let's just say that we had a switch, a mechanical switch that was connected in line with my armature of my motor, which is in parallel with my shunt. This over here would be low voltage release, because if this switch was mechanically closed, if I had a power outage, the motor would shut down. Since the power would come back on, because that switch is still closed, it would operate again. It has been released to go and operate again. These are going to be associated with 2-wire control or 3-wire control. 3-wire control is what we're looking at over here. 3-wire control. 2-wire control would just be where I've got like a thermostat or just a switch or something like that. How do we keep them separate? Go off of the syllables. Okay, how many syllables does this have? Protection. That is 3 syllables, therefore it is going to be a 3-wire type of one. This is just a memory trick. This one over here, release, is 2 syllables, therefore it is going to be a 2-wire. So that's how I keep them straight in my mind. Protection, 3-wire, release, 2-wire. All right, let's go back to the actual operation off of this one now that we have gone through that little bit of necessary knowledge there. Let's talk about this one. Once again, we're going to go and energize my start circuit. So I'm going to press that button. When I close that, I'm going to go and have this complete path for current that is going to go in through here, because we have sealed in this contactor over here. Because I've sealed that in, I've also sealed in the rest of my M1s over here, and I'm going to go and see a couple more paths for current that are going to go down, one through my shunt fields over here, and another one that is going to go through my armature over there. And therefore, I'm going to go and have operation of the motor. If I lose supply voltage, I would lose this and the thing would shut down. If I would press the stop button, I would lose this path over here and all of these would open and would go and shut down. If I were to go and get too much current and this were to get too hot and it were to trip this, I would open this circuit to my contactor, and once again we would go and shut this thing down. What does this thing not protect us from? Well, if I take a look at it, what I don't see inside of here is I don't see anything that is going to go and protect us from loss of field. And we're going to deal with that one later on, but it is not going to go and protect us if we were to go and lose this field. There would be no way for us to know, and because it's a shunt motor, we would have to worry about us getting to unsafe values of acceleration off of it. All right. Let's go and take a look at our next one that we have over here. The next one is going to be an acceleration type of control. And we call this thing the current limit acceleration. We know that Kirchhoff's law of voltage, KVL, Kirchhoff's law of voltage, that's a weird looking L, is that the sum of all voltage drops is equal to my source voltage. So if I'm going to go and apply a value of voltage, let's say I've got 24 volts DC that I'm putting across here. If I were to take a look at this line over here, I would have to drop a full 24 volts across each of those components. So I can go and treat each one as if it were a resistance. In reality, they're going to be made up of 3 different things. I've got my series field, I've got my armature, and I'm going to go and have my actual field resistor that I'm going to go and have over there. That's these 3 components over here. When I initially go and close this in, so I'm not going to go through that control circuit over there. We're just going to go off of the fact that we have got the control circuit figured out. We are going to go and see main current that's going to go and pass through here. It's going to pass through the overload. It is going to go and pass through the armature, and it is going to go and pass through here. Now it is going to have a little bit that could go through here, but there's not going to be a lot that's going to go through here because I've got 2 paths in parallel. They're both coils. And we know that the overall resistance is always lower than the lowest value of resistance. What we have over here is we are looking at our voltage drop. If you remember, we have got counter EMF that is going to go and build up as my motor starts to go and rotate. When I've got 0 RPM, I'm going to have 0 counter EMF, 0 C. Okay. When I get up to my full value of RPM, we're going to go and say that I call this thing rate it. I'm going to go and have full value of counter EMF. The counter EMF is going to be high, or it is going to be full. that I'm going to go and have. So when I start this thing out, I've got no rotation, therefore I've got no counter EMF, therefore I'm going to go and have no armature voltage, hardly any armature voltage initially, and because this coil over here is placed in parallel with it, it is also going to go and have next to no volts. But because I do have current flowing through this series field, through my shunt field as well, I am going to go and have rotation that is going to start, and as my rotation starts, as my RPMs start to rise, I'm going to go and see my counter EMF that is also going to start to go and rise. And because my counter EMF is across this armature, that means that the voltage across here is also going to be seen as rising. And eventually we will get to a point where the voltage across here has risen from 0 volts to whatever value of volts that this coil is designed to pick up at. And at that point, this coil is going to close. Current is going to take the path of least resistance, and we will see our current change over going through here. Now it is going to go through here instead, and we are not going to be sending as much current. There will still be a small amount of current going through that resistor, but it's going to be negligible. The bulk of our current is going to go and bypass, and it's all based upon the amount of counter EMF that I'm going to go and have. It does need to be a designed system. I'm not just going to grab any old contactor, throw that in here, any old resistor. This is going to be an engineered system that is usually going to go and be inside of your specs that you're going to go and get from your motor builder itself. It's going to tell you that if you want to go and use current limit acceleration, you need to go and use resistances of this size, and you need to have a coil that's got a pickup voltage of this, etc. If I want, I can go into multi-stage. This is the exact same thing. It's a counter EMF controller or a current limit controller, and it is going to now go and have two. These are going to go and have different values of voltage that they're going to go and pull in. Let's say that this one here is going to go and pull in at 1/4. This one over here might pull in at 2/3 of my counter EMF. And these are once again going to be based upon the actual motor characteristics itself. But what I would see is that initially neither would be pulled in because we would be at 0 volts that we would have on that armature. When that's at 0 volts, both of these would be open, therefore there would be no shorting out of our paths, and the only path for current would be for it all to go and travel through here. Once we go from 0 volts, we start to build some counter EMF. As the rotation increases, we would hit that 1/4. Once we hit that 1/4, this one over here, because it's in parallel with that armature, would seal in, which would mean that this line over here would seal in, and our current would now go through here and go around like that. So we would lose this first one over here. As it goes through there, now we are going to go and have less resistance. We're going to allow more current through, more acceleration. It would then go up to, this 2/3 that we have. And once we hit the 2/3, this one would go and seal in, and we would have one last changeover of current where now all of my current would be traveling through that path over there, bypassing these two resistors. Once again, has to be built to the motor itself. All of these work off of us knowing things about our motor. We have to know the size of the motor, the armature current, the load that's going to be attached to it, all of that, so we can size these values of resistance and these contactors to them. It's going to take a little bit of engineering. In some cases, if I've got a fixed type of motor, what I might choose to do would be go off of, instead of sensing, I'm going to go off of a definite time, which means that I'm going to start using my timing relays. Timing relays are going to be relays that are going to go and provide a delay between either turning on or turning off. And we are going to go and see them off of these types. Now, you do need to go and learn these ones. You have to memorize these. Guaranteed you will get asked questions about these inside of third and inside of fourth because they are a common part of ours. We are going to go and have our normally open time to close. So we provide power. I'm just going to go and write this out over here. Power. Once power gets applied, there's going to be a timing, ... and then there's going to go and be action. That is going to be for all of these timed to do whatever. Normally open, time to close, power is going to be applied, ... and then we're going to go and have our action. So in this one here, power is going to be applied to the coil, not to the contact, but to the actual coil of this one, the TC. Once it's applied to the coil, it's going to start the timing action, and then boom, this one is going to close. This one over here would be the opposite. We're going to apply power to the action. It is going to start timing, tick, 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 boom. It is then going to go and open that thing up. These ones over here, on the other side over here, are going to be my normally open time to open. And then they're going to go and have where they're going to have action immediately upon power being applied. And then when I go and lose power, then it is going to go and revert. Okay, we're just going to say revert over here, which means change back. So in other words, when I take a look at this timing coil for one of these that's associated with one of these over here, what I would see is that I would get initially action. So as soon as I provide power, boom, this normally open would close. Then we would go and have this thing would stay closed. And as soon as I lose power, I should actually put that in there, loss of power. As soon as I lose that power, then this thing would start timing, tick, 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 and then it would revert. It would go back to being normally open. So it's normally open when it's de-energized. As soon as I energize it, it closes. It stays closed until I lose power. Once I lose power, it starts timing, tick, 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 and then boom, opens up. This one over here is going to go and be opposite. We're going to go and have, once again, the second that I apply power to this coil, it is going to go and operate. So it's going to go and open. And then it's going to stay open until I lose power to the coil. And when I lose power to the coil, it's going to start timing, tick, 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 and boom, it's going to go and close once again. Normally closed, timed to close off of these. These can be operated by multiple different timing methods. We can either go with electronic timings or we can go with a couple of older ones. We're going to go through these real quick because they are pretty much useless to us. First one over here is going to be dashpot timers. It used to be one of our better methods of maintaining. It was a sealed system where I had a thick, viscous type of fluid over here that was going to be placed inside of here. It was going to be inside of a sealed cylinder, and there was going to be a small orifice or opening that was inside of there. When I would go and provide power to this, it would go and, it would try to pull this thing up, but it's going to be jammed because there's all this thick fluid on the top over here, and it has to get forced through here. So it would take it a little bit for it to pull all the way up. Eventually, when it pulled all the way up, it would be able to go and push this contact over here and change state. It would do the same thing when I would lose power over here, then this thing would have to go and settle back down. It would take a while for this thing to go and time down. They were called dashpot timers. You had to go and maintain the oil levels and stuff inside of here, make sure you had no leaks, etc. And they were bad when I had changing temperatures. Because if I had changing temperatures, the viscosity or the fluidity of that fluid would go and change. Think about molasses. If it's going to be cold, it's going to go and take forever to go and flow. But when you heat it up, it's going to move much faster. Or engine oil, same thing. It's going to go and flow slow when it's cold. When it's hot, that stuff, it gets super runny. So my timing would change because when it's super runny, it's just going to whoosh, fly through there. But when it's super cold, it would be really, really slow. The other one that we had was pneumatic timers, and the pneumatic timers was going to go and have just a bellow. It was literally going to be a bellow that we were going to go and take in outside air. This over here was my needle valve. The needle valve, I could go and back this thing off and increase the size of the air channel. Once again, when I would go and energize the solenoid, it would attract the armature, and the armature would have to inhale, but if it had a very small straw to inhale with, then it would not be able to inhale very quickly. So it would take it some time, and as the bellow would push up, it would operate my set of timing contacts. When I would release, same thing, it would have to go and push it out through a check valve, and the check valve could be timed as well. You could also have needle valves on the output of that. Once again, it was a way to go in time. It was an old way, and it was bad inside of dusty environments, because in dusty environments, this air inlet would clog up, and my timing would change over top of time. Look at how old the pictures are. That should tell you how old these things themselves are. What we more commonly have is we have got electronic timers, which you go and use an RC timing constant inside of there somewhere that is then going to allow us to adjust. Now, sometimes you will see ones like this that are very simple, where they're going to just have a dial on the top. In a lot of cases, they're going to go and have multiple different types of components that are going to be placed inside of them, where we are going to go and have different dials. We can adjust this thing. Is it going to be an on delay, off delay, etc. Well, actually, I think we covered these in second. We gave you some of these to go and play around with in second year if you took it here at UFE that were part of your motor controls. They are going to go and fit into regular, what we refer to as DIN type of bases that are going to go and snap onto that control thing that we call DIN rail. It's got a profile that looks like this. We mount it to a cabinet, and then we can snap these components on and off of it. That's just kind of our side view of what the DIN rail itself actually goes and looks like. Yeah, it looks something like that. Slot it, we'll mount the stuff inside of our cabinets. This is also a little bit off. This thing should be cammed around. The keyway is always going to be, towards one side of these things. This is going to be what we refer to as an octal base or an 8-pin timer. We're also going to have these things available in 11-pin timers. We're usually going to have to go and have constant AC that is going to be applied to these and a control. This one that they're showing over here just shows a regular AC where we would have to go and store charge inside of here. We don't have a lot of them where we're going to store charge because that's unreliable. Most of these we're going to have constant AC. And instead of us having all of these associated with controls, we might have a bunch that are associated with controls, and these ones over here, which would not be relay contacts, but I would use, 5, 6, and 8 in, some of these to go and be my signal. And my signal, it would be basically just an input that I would go and follow. This input, when the input goes high, it's going to start its timing. When the input goes low, it's going to start its timing. If it's going to be a to off delay, etc. All of these, doesn't matter which one you're going to go and use, can be utilized inside of timed circuits over here. Definite time acceleration. Definite time acceleration is going to go and involve us just placing this timing relay into our control circuit. You'll note that's the big difference. It's being placed in parallel with this motor circuit. And I'm going to go and use in this one an on delay type of timing that I'm going to have. I know that if I take a look at this, this is NOTC, right? Normally open, that's what it is right now, timed to close. The arrow is telling me that this thing is going to go in time to close over here. What I would see when I go and activate this is as soon as I go and start this control circuit, I'm going to have current that's going to go through my main coil as well as through my timing relay. So my timing relay at that point is going to dot, dot, dot. It's going to start its timing. Because it's starting its timing, I'll erase that so we just have room. It is going to not have activated yet, which means that because I also sealed in with this M at the same time, I'm going to have current that is going through this resistance over here. Also going to have current going through the field. We're not going to forget that. But I'm going to have current going through my series field, my armature, and this resistor. But this thing, when we energize it, it was dot, dot, dot. And when this thing has finished its timing, it is going to close this contact over here. And my current path is then going to go and change over, going through like that over there. My current path is going to go and take the path of least resistance. We won't have a lot of current that's traveling through our resistor anymore, but we will still have our armature and our series field, which are going to be utilized over here. These ones, I do need to go and be careful that I set the timing up correctly for what the acceleration is. And if my load changes on my motor might not have come all the way up to speed before this resistor gets kicked out. And in cases like that, it could be that we'll never, that it's not going to have enough torque to go and develop, and it's going to go and stall out. It can be a little bit of an issue, but it's usually not going to be much of an issue because in a lot of cases, once again, this is an older style of control inside of here. We don't want to necessarily use these timers. What we oftentimes at this point do is we just monitor our armature current. We're going to go and use a current sensing. That is, as my current goes down to certain levels, then we're going to be able to go and kick in, this over here. It's just going to be a current sensing relay. Let's talk about this one over here. Oh man, if you can't buy a timer, why don't you just go and build a timer? This seems like a terrible plan. Because most of you aren't going to understand what's going on when you're starting to go and build these ones over here. Let me just take a look at this thing in two states, energized versus de-energized, okay? When this switch is closed up top over here, but when I have not energized my control circuit, I will have paths for current going through like this. There's going to be a path for current going through here. So that AC is going to be always on, which means that this is going to be open. It's a normally closed type of contact, but it's going to go and sit open. I'm also going to go and have current that is going to go through this capacitor like that. So this is going to go and happen at all times when the starting circuit is on. This cap is going to go and charge up to a value that is going to go and be my full DC line. It's going to go and have this, whoop, where it charges up like that. We'll charge up to a full DC line. So if this is going to be 24 volts, this will charge up to 24 volts. What happens then is this cap is going to be built up. So I'm going to just draw that now. The current flow will happen until the cap builds up. We're going to stick a bunch of electrons and a bunch of holes on this side over here. When I go and energize my circuit, a bunch of stuff happens simultaneously. This is going to go and close in, right? We seal that in. M contactor here is going to go and energize. When M contactor energizes, this is is going to open up here. This is going to go and open up here. These are going to close here. These are going to go and close here. And what happens is we're going to have two different current loops. First current loop that I want to talk about is going to be my capacitor discharge. As soon as this opens up, my capacitor is now no longer being held across the lines, but my capacitor is going to go and try to send current through this path back to the holes on the other side. So the cap is going to start to discharge. Note that it's sending its current through this AC, my acceleration control relay, in the same direction as what my supply was sending that current through earlier as well. So we are going to go and see that current driven through in the same direction, which means that this is still going to be energized, which means that these are still going to be sitting open right now. If those are all sitting open right now, that would mean my only path through the armature would be like that, going through that resistor. But as this cap sends electrons over and depletes its value of voltage from one side to the other, the value of current that is going through this discharge path over here is going to go down. It's going to go down, 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 down. As that current goes down, we're eventually going to hit a point where this is no longer going to go and have sufficient amount of current to go and hold this contactor. At that point, this contactor is going to de-energize. When it de-energizes, it goes back to its initial state of being normally closed, and my armature current is going to go and travel through this path at that point. Yeah, so why not, instead of going and buying a timer, why don't we just go and build a timer? Guys, you will probably never build one of these, unless you had a DC motor that was going to be the same every single time. It would be absolutely pointless to go and build one of these. Usually, like we've said before, we're just going to go and monitor the current. And you would have to go and make sure that this, is going to go and be sized to the motor. You'd have to know what your motor is, what your load is, etc. They do tell us that if we wanted, we could go and change that to a rheostat. If we would change that to a rheostat, we could vary how long it would take for this thing to discharge, which would vary how long we would go and keep that resistor inside of there. It's going to be fairly rare. Doubt you're ever going to run into one to fix, much less be asked to go and design one. But it's part of our curriculum that we're supposed to be teaching this stuff. So there you go. Okay, let's talk about field loss protection. This is an important part of our DC shunt motors, because we know that if the DC shunt motor were to go and lose its field, that we would then go into this dangerous overspeed, some runaway that we would have on that motor. What we will see a field loss relay that at times will be electrically placed in series with this. Sometimes people say, well, why don't I place this thing around the outside instead of seriesing it? The problem would be then that if I have an open inside, this thing would still be line to line, so it wouldn't actually be protecting anything. We place it in series, it is going to go and be a very low power type of relay. We want this thing to just be a weak relay so that we don't drop a lot of volts, because we will have to drop Kirchhoff's voltage law, some volts across each of these. So if I've got a 24 volt system over here, what I might have, let's go to a 90 volt DC, they're more common. A 90 volt DC system over here, I might be dropping 10 volts across here, which would mean I'm going to be down to 80 volts across here. So I'm already going to have a slightly weaker shunt field. Placing one of these in line does mean that I'm going to be a little bit above my base value of speed over here. What you have to do is you have to match it as closely as you can, once again, to your shunt field over here. And if my shunt field were to go and drop out, as soon as that thing would drop out, I have no complete path for current through here, which would mean that this set of contacts over here would go and open. And it's just going to go and kill my control circuit. We would see that the control circuit itself would go and drop out. Let's look at it just as a good circuit over here. If it was a good circuit over here, what I would see is that when I press my start contact, I'm going to go and get current that would travel through here. That current would energize this coil over here, which would close in. When I would close in that coil, these would all energize and current would pass through my fields loss relay as well as through my armature. So I have motor current that's happening. This would also then close. I could take my finger off the push button at that point and it would be fine, because I would still have current that would be going through this path over here, through those. But as soon as I were to go and lose this field, I would lose energization on this field loss relay, which would go and kill my motor itself. Reversing, they have just brought up in here again. We're not going to bring it up in here or go through it much. We know that reversing of a motor is going to go and be done through interchanging of my direction of current through the armature. We would have to go and have something that would interchange that. It's going to be forward reversing set of contacts, and you're going to have to make sure that you do that without plugging or applying your value of voltage in the opposite direction. Okay, last one that we're going to talk about, compound motor with time limit acceleration and speed control. Two separate things that we're combining. First thing that we're combining, we've already talked about. That's going to be this circuit over here. That is going to be my time limit acceleration, where I'm going to have that timing relay. What type of timing relay? You should be able to identify this as on delay. On delay, like that. Which means that when I provide power to this, we're going to go power, tick, 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 timing, and then operation. So when we provide power to the start circuit, closes in all of these, gets this current flowing through here, it is then going to start timing, tick, tick, tick. Once the timing has completed, it is going to close, and it will send all of our current through here. The other component that we have inside of here, so we've talked about that previous one, is just going to be my field rheostat that we see over here, and that field rheostat is being used to give me operation above base speed, right? As we increase our value of resistance, we are going to go and go above base speed. Note that I'm not using a field loss relay inside of here. Because if I go with a field loss relay, I would have to go and size now the field loss relay with my shunt field and with this field rheostat. If I go to too high of a value of field rheostat, I would go and not have sufficient current going through to hold that field loss relay in. In a lot of cases, when we need to go above base speed, we're going to go and have mechanical overspeed protection, that we would go and use. That mechanical overspeed protection, we would just place a normally closed contact from that mechanical overspeed protection in line with this, so it would be able to go and shut that motor off. All right, that's our DC speed control. It's relatively straightforward. We've been looking at acceleration. We're going to start taking a look at deceleration next.